My name is Professor Santiago Aparicio. I'm the leader of the Materials Design Group at the University of Burgos, ICRAM, and welcome to the chapter on computational techniques for material designs and CO2 capture and conversion processes. The objective of this chapter is to show the application of in silico methods, where in silico means the use of computational techniques for designing materials. And I will try to answer three main questions. Why we do this, what is the objective of this kind of studies, and how we approach to this problem using computational technologies. The first relevant question is answering why. Why we are considering in silico methods for designing materials. We should have in mind that designing advanced materials is essential for developing new technologies, new economic materials, and for answering societal challenges like clean energy and environmental problems like the CO2 capture and conversion problem. We should have in mind that advancing and designing new materials is a long-run process. Since a material is discovered at the lab scale level, until it reaches the market, the massive production, it may take up to even 20 years. So it's a process that requires a long time. The objective of using in silico methods for designing this material is to decrease this time and to design materials specifically designed for each application, in this case for CO2 capture operation. Basically, this in silico methods allows the acceleration of the material design and decrease the cost. Designing a new material is extremely cost operation, and using predictive methods based on computational methods decrease the cost, then it's a clear increase in the competitiveness of the process. Therefore, this approach is not excluding, obviously, experimental studies, but is complementary in order to decrease the cost and increase the rate of material design. What are we searching in the case of CO2 capture operation, in the case of new materials for CO2 operations? Basically, what we are looking for is materials which show high affinity for CO2, a material that is able to capture the gas from gases coming from power plant or even from the atmosphere, in case we need to design operations for direct air capture operations, and also these materials having a certain group of complex characteristics. The first one, they must be low-cost materials. Carbon capture and conversion operations are costly operations in terms of increasing the power production. So it may take an increase of up to 30 or 40% of the final cost of the energy produced. So these materials should be produced at very low cost. They should have physicochemical properties suitable for the design of this large-scale operation, in terms of viscosity, in terms of heat transfer, in terms of mass transfer. So they should allow their scaling up, not materials that only work at lab scale. And these materials should be safe by design, so they should have low environmental impact and low impact on human health. We are trying to solve a problem, which is the presence of carbon dioxide capture in the atmosphere because of human operations, and we should try to minimize this problem using environmentally friendly solutions. Basically, in silico methods, those methods based on computational resource, are able to predict the properties, to predict the affinity of the materials for CO2, to predict relevant properties required for process design, like viscosity, like thermal properties, like mass transfer properties, and are also able to predict impact on humans and environment. The main advantage is that we can carry out all these predictive studies, screening literally millions of materials at no cost. So basically what we prepare is fictitious materials, predict their properties, and see if they are able to fit according to the needs of this specific technology. How we do this? For solving this problem, or for solving any problem which require material design for a specific operation like CO2 capture, we carry out studies in which we call multi-scale materials modeling application. We do not have a single methodology for covering the whole material design process. the complexity and the different needs of the new materials requires different theoretical methods. Basically, to cover the two types of scales that we have in this kind of problems. We have a time scale, in which we should consider at which time occurs the different physicochemical phenomena, going from the, let's say, picosecond, 10 to the minus 12 scale, to the second, hours, or even days scale, so very, very different time scale. And the second scale is the spatial scale. The physicochemical phenomena, the phenomena involving carbon dioxide capture and conversion, goes from the angstroms or even nanometer scale to the micrometer, to the meter or large scale if we consider industrial application. So basically we have a different scales from the nano to the micro to the meso or to the macro scale, which require different methods. The usual approach is starting from the design of materials at the lowest level, at the atomistic level. Starting from this atomistic level, we consider methods based on quantum mechanics. Quantum mechanics allow to develop very, very accurate predictions, but they are extremely time-consuming. Simulations at this scale using this method can be applied only to a small number of atoms. So, for example, we can study the interaction of small groups of atoms describing the main properties of the materials with carbon dioxide molecules in order to predict the properties, in order to predict, for example, the affinity, the ability of the materials to bind to the carbon dioxide, which is pivotal for describing, let's say, the ability to capture the gas. These methods, these quantum-based methods, cannot be extended beyond, let's say, a few hundred atoms. So if we need to describe properties which require a larger number of atoms, we have to go up in the scale, going to the next step in the nanometer or micrometer scale, in the nanosecond or microsecond scale, using methods like molecular dynamic simulation. Molecular dynamic simulations allows to study, let's say, even millions of atoms, groups of millions of atoms, and they are not quantum-based methods. They are based on classical Newtonian mechanics. So they are, let's say, less accurate, but requires or allows the application to a larger number of atoms. They allow us to predict relevant properties like viscosity, like diffusion, like the behavior of mixtures of CO2 with the absorbent materials, but they have some limitations in terms that they are based on what we call force fields, which describe the interaction between the different types of atoms and molecules present in the system. If we need operations or if we need properties requiring, let's say, larger numbers of atoms or phenomena which happen, let's say, at the seconds or multi-second scale, it's not able to apply molecular dynamics method because the time requirements are too large. So we go to what we call mesoscale or macroscale methods like finite elements modeling, like computational fluid dynamics, or if we go to the top of the scale, methods based on what we call process design methods. All these methods do not consider specific atoms, electrons, or molecules. They consider groups, areas of the material which are described through simplified approaches. Obviously, they are much less accurate than the other ones, but allow us to infer with a reasonable accuracy properties required for describing the materials. The main advantage of this multi-scale modeling approach is that it can be carried out, let's say, in a bottom-to-up approach. We can obtain certain information starting from the atomic level, which fits the next step, fits, for example, the molecular dynamics level, in order to develop the force field which are required for the simulation. And these results from the microscale level can fit and can allow us to design the upper scale level modeling. So in this way, although each level of the scale give us different information, they are fully complementary. In this way, we can predict all the required properties for the selected materials according to all these needs. So basically, in this approach, we are able to screen multi-million number of atoms, or molecules, or systems, or materials, predict their properties, and select their properties according to the needs, according to the design needs, in order to fulfill the requirements for CO2 operation. Obviously, the screening of this material using the 6 silico methods will lead to a reduced number of materials with the target properties, with the properties selected according to the need, which will be obviously finally synthesized in the lab and going up in the scale for a final process design. But it allows us what we call a task-specific design for a purpose, which in this case is carbon dioxide operation and capturing and conversion processes.